So let's start with one very simple thing. The word quantum, I'd say as it has been used for the last 7 years in the general press, and here I'm talking NPR, New York Times, Wall Street Journal, all of these, has meant quantum computing. Yes, quantum is other stuff, but quantum computing has gotten a tremendous amount of press. Part of this, the program I was involved with at IBM before this, IBM did an awful lot in terms of marketing and reaching out to the press and so forth. Because, quantum is weird, and when you have companies like IBM and Google and Microsoft and Amazon who want to sell you the next big thing, they're going to reach out. And oh, by the way, you also have things like Ant-Man, right, with quantum mania, and it gets a little crazy at times. And so one of the things I like to point out to people is that this quantum thing has been around for a really long time. I mean, if you want to go way back and look at the science, people like Max Planck, right, in 1900, and Einstein, things like this. But this, over the last, let's say the last 40 years, if you've ever had an MRI, shoulder problem, knee problem, whatever, known somebody, that is a quantum machine. It's a quantum phenomenon. Luckily, they don't use lasers to do MRIs, because that would hurt. I'm sorry, it's a different conference. But it's part of people's everyday lives. And the reason is because, well, it was safer than having a lot of X-rays, but it also at higher resolution than X-rays. And this is one of the things when you really start getting into all the different quantum technologies, you start realizing that these types of technologies, we're going to talk about sensors and clocks and computing, are about as good as we're going to get for a lot of these sorts of things. So there was a brief presentation this morning about the CHIPS Act. Now, why did we need a CHIPS Act in the first place, right? Everything just didn't disappear offshore magically, right? I mean, decisions were made by people, right, to do that. So it was to, let's say, rebuild the American semiconductor, but also, as all of us keep saying, and photonic and quantum, right? And things like this. But with so many of these technologies, if we mess up with quantum, we're not going to have another shot. There's not a follow-on technology to quantum that is better than quantum for many of these things. So on one hand, that's a great business opportunity, but we better not screw it up. And so that's important to remember, right? And so we don't do too much. So let me also say, in giving a talk like this, the title is pretty generic, Quantum 101 for Business Leaders. Inflection is a sponsor. I've got it right over here. And in order to talk about quantum and what people are doing with quantum, I could talk about all of our competitors' products, but I typically don't do that. So I'm going to try to keep at an appropriate comfort level about mentioning what inflection does as an example of things. And use it not so much to sell you anything or market it, but to give you an idea of why we do what we do. There's got to be a reason, right? And so when you're in business, why are you in that business? It's not just to make money, right? I mean, that might be okay, but you're fulfilling some need. You're trying to get the world from here to there in somehow. And so with this, I'm trying to bring 3 ideas into this. So in the middle, we talk about quantum enabled. Okay, that sort of makes sense. We're using quantum technologies to do something different, to be at the heart of the technology and what we're trying to accomplish. Software configured. All right, now I come from much more of a math and computer science background. I'm not a hardware person. I've had to learn more about hardware. You're very interesting people, I must say, right? But I'm a software guy. And hardware really sings and does things when you have great software on top of it. iPhone, all right, 20 million apps, right? Great hardware, lots of innovations, but it's going to be the software. And so just as software has driven what we call classical computing, so these types of processors, as well as laptop supercomputers and things like this, ultimately software is going to drive not just what we do in quantum computing, but in all the other types of devices. So we have to go above that, and I think to a very large degree that has been ignored. That is, we build the software we need to control the low-level hardware and then make do with some engineering things. But where is the software stack on top of sensors? I don't mean the little layer of code. I mean the whole stack, right? How do these communicate with other devices? And there's a richness to this that as we think about quantum and as we think about photonics and how we connect these things, it becomes much more interesting. And there are parallel problems to what we're trying to do in hardware. And the third idea is the edge. And so really, when we talk about computing, you can look at it different ways, but if you think about cloud computing or data centers, there's the type of computing that happens in these great big data centers with many, many servers, right? And things like this, and they can munch on a lot of data, and they have lots of blades and processors. And then the edge is almost everything else, right? So it's what happens in a cell phone tower. For defense, it's the types of things that people in the military have. But it's also satellites, right? It's also IoT, it's your thermostat, it's all these other interesting things. And that's where a lot of the data comes from, right? Because computing isn't just about great processors, it's about data and doing something interesting with it. Much of the focus on quantum computing to date has been focused on trying to build quantum supercomputers. And we are a long way off, a long way off. And I'm going to get to some of the reality checks on quantum computing in a little bit here. So a quantum supercomputer doesn't live in a cell phone tower or anywhere else. It lives in a data center. But as we all know, computing spreads out. This was a supercomputer 30 years ago, right? Why should we expect anything else with the computers and the other quantum-enabled devices? But we're not going to get there by ourselves. We need photonics. We need you all to make it a heck of a lot smaller and a heck of a lot cheaper. And that's how we're going to get the ubiquity of photonics-enabled quantum devices, of which we'll now start to see what those are. So the types of markets to which we're driving these things. First is, let's talk about traditional PNT, position, navigation, and timing here. I have to admit, I was very sheltered. I had to look up what PNT meant the first time I saw it here. You just don't use it when you're selling to enterprises, right? Software to enterprises. But there's some interesting things with it. I mean, your phone has an accelerometer in it. Your phone has a compass in it. They're really cheap, they're really inaccurate. When you are talking about military planes and ships and submarines, when you're thinking about cars, all sorts of things, you need far, far greater accuracy. And you need things like atomic clocks that last a long time, that are stable for a long time. The GPS satellites that are up there have to be synced twice a day with ground-based atomic clocks, the best one of which is about that way, 15 miles, right? Which is why you're all here. Enhancing the security and efficiency of global communication networks. There's a lot that goes into networks. It's easy to say security and whatever that means. Most of the time when quantum comes up with the word security, it's as a bad thing. And I'll talk about that a little bit. Quantum breaking encryption, right? You may have heard of Shor's algorithm and so forth. But there are ways of encrypting data so that you can tell if anyone has looked at it. It's a big area. And also efficiency. Timing of networks is the working of networks is very dependent on timing. If I am sending different packets of information out, well, they better arrive in the correct order, and we've largely figured that out because it's kind of slow and it's not too hard to do. But when you're doing high-speed financial trading, right, or you're optimizing an energy grid, right, because then if the timing's off, things might kind of explode, right, you have to make this work. And this is the third point too, because whereas we used to think, well, there was a nuclear power plant down the street, or a long time ago, coal-fired plant, right, or whatever. Now there are so many different sources from energy, and even if you have solar panels on your house, not only are you receiving energy, you're pushing energy back onto the grid. This has become a massive optimization problem. So quantum can play in the infrastructure as well as the computing aspect of how you optimize how all of this is working, because they're very, very hard problems to do.